All right, everybody, welcome back. We are going on to our third topic of trigonometry. We did the study of angles. We just completed the study of how to use trigonometry and apply it to solving triangles, both right and oblique. And now we move on and we get into the algebra concept of trigonometry. This part of trigonometry is the graphing. We're going to physically bring to life what a sine, a cosine, a tangent, and their reciprocal functions look like. The first thing I need to do is introduce you to a new word in your notes. So your new word is periodic function. Sine and cosine and tangent and our other three reciprocal trig functions are called periodic functions. And what that means is that they have a pattern to them. So when you graph them, the pattern continues on and on in both directions, left and right. Now you're going to say, why is that important? Well, let's think about it in real life. If you go to the beach, the tide comes in, the tide comes out. That's periodic. There's a pattern to that. People that study the oceanographers know that pattern. There's a pattern to temperature. So meteorologists understand when the high is and what the low is compared to each season. There's a pattern to that. So that's what happens here in trig. Your heartbeat goes ba-dump, ba-dump, ba-dump. There's a pattern to that. That's periodic function. So that's important that you know, because when we graph these trig functions, they can go on indefinitely both to the left and to the right on the x-axis, and that pattern would continue. Now, all these functions we graph, these 6 trig functions, are curves. So we're going to learn how to graph curves. Well, to go back to graph trig functions, we got to go back to the beginning. When you go back to the beginning of equations from Algebra 1, to graph, you learn to set up a t-table. So if you remember, I'm going to throw something up here quick that's not in the notes. If I gave you the equation 3x plus y equaled 6, and I want to graph that equation, in Algebra 1, it's a linear equation. One of the first ways you learned was to set up a t-table. You pick a number for x, you sub it in, you get a number for y. And we know we could pick any number we wanted for x. So if I picked x as 1, I would sub it in, substitute, I would do 3 times 1, and I'd get 3 plus y equals 6. And I'd solve that for y by subtracting 3, and I get y equals 3. And that t-table would help me form an ordered pair or a point or a coordinate. And then I'd get enough of these ordered pairs points and connect the dots, and lo and behold, I would have a graph of a line. Well, we could do the same thing in trigonometry. Because you've never graphed a trig function before and you have no clue what it looks like, we're going to start with basics. We're going to do a t-table. So the trig function I want to graph by hand is y equals sine x. So because we're graphing, not only are we using an x, but now we're using the variable y, because we need our x and y axis. What I want you to know is, just like when we do a t-table for a linear function, we're going to substitute in, we're going to pick a number for x, substitute it in, evaluate our expression, get a number for y. The key difference here is, because we're graphing trig, this number for x is an angle. Remember, trig, sine, cosine, tangent, its reciprocals, the definition is they're a relationship between an acute angle. So when you write sine and you put an x behind it, that x represents an angle. Well, what have we learned about angles? What units are they measured in? That's right, they're measured in 2 different units, degrees and radians. Which one do you feel more comfortable with? I agree, degrees. So when I do my t-table and I'm going to pick values of x, I'm going to use degrees. I'm not going to use radians. That's the first thing, because I feel comfortable doing degrees. Secondly, when I pick my angle measurements, they got to be angle measurements I could look up without a calculator, because I want to go quick and efficient. I don't want to sit here and pick an angle that I need my calculator to look up. So if I'm going to look up angle measurements without a calculator, going back to the previous beginning of the semester here, we're going to need our buddy, the unit circle, and our special right triangles, our 45, 30, and 60. So first thing I'm going to do is label my unit circle. On the unit circle, we deal with what kind of angles? That's right, quadrantal. So this is 0 degrees, 90 degrees, 180 degrees, 270 degrees. And you should have memorized the coordinates at each location. So at 0 degrees, the coordinates of the unit circle are 1, 0. At 90 degrees, they're 0, 1. At 180 degrees, they are negative 1, 0. And at 270 degrees, they are 0, negative 1. And we know on the unit circle, x represents cosine, y represents sine. All right. But we can also look up angles that are not quadrantal using our special right triangles. We know we can look up the sine, cosine, and tangent of 45 degrees because we have memorized the relationship of the sides of this special right triangle. Because it's a 45, 45, 90, we know the two sides are equal in length, so they're each 1. And we know by doing Pythagorean theorem, a squared plus b squared equals c squared, we know the length of the hypotenuse will always be the square root of 2. And now that we have that right triangle, we could do sine, cosine, tangent, doing our definitions, x over r, y over x. For 30 degrees, we know the side opposite is 1. We know the hypotenuse is 2, and the side adjacent is square root of 3. For 60 degrees being our acute angle, the side across from 60 degrees is square root of 3. The hypotenuse is 2. That means this adjacent side is 1. Not only do we need that information, we also need our little code words. So we have one more reference we need to know. We need to remember all students take calculus to know, depending on what quadrant our angle is, depends on whether our trig function is positive or negative. We also have to know if an angle is bigger than quadrant 1, then we need to make its reference angle. So we need our reference angle rules. In quadrant 2, our reference angle rule is 180 minus theta. In quadrant 3, our reference angle rule is theta minus 180. And in quadrant 4, our reference angle rule is 360 minus theta. Yes, people, I expect you from the chapter 1 to remember all this. This is the basis of trig, knowing all these definitions. So we should use them as much as we can. So now we're ready to rock and roll. So for me to pick an angle here, I'm going to start with the lowest angle, 0 degrees. So I want to look up the sine of 0 degrees. So I go to the unit circle, sine is y, the y value is 0. And I'm going to put that in my chart. I gave you x, you give me y. Now I'm going to look up the sine of 30 degrees. I'm not going to use 10 or 20 because I don't have a reference to look them up. I would need a calculator for that, and I don't want to rely on a calculator. So I'm going to do the sine of 30. 30, sine is y over r, so that gives me a half. I'm going to do the sine of 45 degrees. 45, sine is y over r, but I don't write 1 over square root of 2. I rationalize that to be square root of 2 over 2. I'm going to do the sine of 60 degrees. 60 degrees, y over r, square root of 3 over 2. 30, 45, and 60 are in what quadrant? Quadrant 1. What do you know about the sine value in quadrant 1? A means they're all positive. Good. Now I'm going to do the sine of 90 degrees. Well, I got to go to the unit circle. The sine is the y value. The y value is 1. Now, we got to look up 120 degrees. Well, you're going to say, it's not here, Miss Black. You're right. But remember, what quadrant is 120 in? It's in quadrant 2. So we're going to make its reference angle. 180 minus 120 would be 60. So to look up the sine of 120 degrees is really looking up the sine of 60. So I go to 60. Sine is y over r, square root of 3 over 2. I want to look up 135. That's in quadrant 2. So I need the reference angle. 180 minus 135 is 45. Sine is y over r. I do not write 1 over square root of 2. I rationalize and write square root of 2 over 2. I'm going to look up 150. That's in quadrant 2. So 180 minus 150 is 30. The sine of 30 is y over r. That's 1/2. Now, everybody look at me. These three angles were in what quadrant? 2. What do we know about the sine value in quadrant 2? Is it positive or is it negative? S means sine is positive. So these three functions would stay positive. Okay, I'm going to look up 180. That's on the unit circle. Here's 180. Sine is the y value. It is 0. I'm going to look up 210. Why 210? Well, it's an angle in what quadrant? 3. I can get its reference angle. 210 minus 180 is 30. The sine of 30, y over r, is a half. I'm going to look 225 up. What quadrant? 3. 225 minus 180 is 45. Sine of 45, y over r. I do not write 1 over square root of 2. It rationalizes to be square root of 2 over 2. 240 is in quadrant 3. 240 minus 180 is 60. So I'm going to look up the sine of 60, y over r, square root of 3 over 2. All three of these angles, 210, 225, 240, were in which quadrant? They were all in quadrant 3. In quadrant 3, is sine positive or negative? Well, T stands for tangent. Tangent's positive, which means these values are negative. Okay, you see everybody tying in? All right, we got some more to go. I want to look up the sine of 270. That's on the unit circle. Here's 270. Sine is the y value. It's negative 1. I'm going to look up 300 degrees. Well, 300 is in quadrant 4. So what's the reference angle? 360 minus 300 would be 60. Sine of 60, y over r. Square root of 3 over 2. The sine of 315 is in quadrant 4. 360 minus 315 is 45. 45 is y over r. We don't write 1 over square root of 2. We write square root of 2 over 2. 330 is in quadrant 4. 360 minus 330 would be 30. The sine of 30, y over r, is a half. All three of these angles were in what quadrant? 4. According to quadrant 4, is sine positive or negative? Well, C means cosine. Cosine's positive, which means sine is negative. And to finish it up, we'll go around in a circle to 360. 360 would be if the terminal ray lands where the initial ray is. So the sine of 360 would be like the sine of 0. This y value is 0. So again, what we did right now is we want to graph this first trig function, sine x. We've never graphed the trig function before. We have no idea what it should look like. So we go back to basics. To graph in algebra, you set up a t-table. You pick a number for x, it spits out a number for y. The difference here is because we're dealing with trig, x represents an angle. So what I did is I picked angles I could look up without a calculator, because I don't want to get those crazy long decimals to graph. Make sense? I picked angles that I know I could look up off the unit circle and off the right triangles. Or I picked angles in quadrant 2, 3, and 4 that I know when I get their reference angles would be off the right triangles. I made sure I knew whether answers were positive or negative by looking at all students take calculus. So now all we have to do is we have our x values, we have our y values, is set up our graph. But here's the catch. When you set up an x and y axis, back in algebra the x-axis was numbers and the y-axis is numbers. Well, that's true in trigonometry too. When you graph the x and y-axis, both have to be numbers. We've already discussed this. Is an angle written in degrees a number? No. So in order to set up your x and y-axis, you can never label your x-axis in degrees. That means your x-axis always has to be labeled in what units, people? That's right, radian measure. So that's why I have an extra column here. because this is degrees. We're about to change all of these degrees into radians. Now, that's a lot of conversions. We learned in the previous chapter to change from degrees to radians, you multiply by pi over 180. What I'm going to tell you in this chapter is you just got to start memorizing things. There are facts you just need to know for trig off the tip of your tongue, especially if you're going on to higher math calculus. Okay? 0 degrees in radians would be 0 radians. That's not going to change. 30 degrees in radians is always going to be pi over 6. How do I know that off the tip of my tongue? Because we talked about this. Pi represents how many degrees? 180. And 180 divided by 6 is 30. So what would 45 degrees be in radians? That would be pi 180 divided by 4. What would 60 degrees be in radians? That would be pi 180 divided by 3. Makes sense? 180 divided by 3 is 60. What would 90 degrees be in radians? That would be pi 180 divided by 2. Those you just got to have memorized. They're going to be used so much in this chapter. All right, 120 degrees. Again, you don't have to go through the long conversion of pi over 180. You got to think for a minute. 120 is a multiple of 60. Do you agree 2 times 60 is 120? So we know we're going to do 2 times, and 60 is pi over 3. So this is 2 times pi over 3. 135 is a multiple of 45. How many 45s are in 135? That's right, there's 3. So this would be 3 times 45, which is pi over 4. 150 is a multiple of 30. How many 30s make 150? 5. So this would be 5 times 30, and 30 is pi over 6. We know 180 is always pi, because that's our definition. Okay? All right, 210. Is 210 a multiple of 30, 45, or 60? That's right, it's a multiple of 30. How many 30s make 210? 7. So this is going to be 7 times 30, and again, 30 is pi over 6. Isn't that fun? It's easy. 225. Who is it a multiple of? That's right, 45. How many 45s would you have to add to make 225? Anybody know? That would be 5. So this would be 5 45s, and 45 is pi over 4. 240. Who is that a multiple of? It's a multiple of 60. How many 60s make 240? That'd be 4. So this is 4 60s, and 60 is pi over 3. 270 is a multiple of 90. How many 90s make 270? 3. So we need 3, and 90 is pi over 2. 300. Who's it a multiple of? 30. How many 30s get to 300? You would need 10 30s, right? 30 times 10 would be 300. So I need 10 30s, and 30 is pi over 6. Now, can you leave that radian measure as 10 pi over 6? No, it needs to be reduced, right? It would reduce, you would divide by 2, and you get 5/3. 30 also is a multiple of 60, right? How many 60s make 300? 5 60s make 300. So you could say, okay, this is 5 60s. 60 is pi over 3. So either way you look at 300 as a multiple of 30 or a multiple of 60, you're going to get the same radian measure. 315 is a multiple of 45. How many 45s would you add to make 315? That would be 7. So it's 7 times 45, which is pi over 4. 330. That's obviously a multiple of 30. How many 30s do you need to make 330? Well, I believe that would be 11, right? So that would be 11 30s, and 30 is pi over 6. And 360, well, isn't 360 just two 180s? So if 180 is pi, 360 is 180 plus 180, which is pi plus pi, which is 2 pi. On that list of radian measures, the ones you're going to see the most that are going to come up in this whole unit are 30, 45, 60, 90, 180, 270, and 360. So those are the ones you should memorize. You should know 30 degrees is pi over 6, 45 degrees is pi over 4, 60 degrees is pi over 3, 90 degrees is pi over 2, 180 is pi, 270 is 3 pi over 2, 360 is 2 pi. But you're going to need radian measure because when you set up your x-axis, you're not allowed to put degrees on there because degrees is not a number. You have to label the x-axis in radians. So now, guys, look. We have all our x values. We have all our y values. We're ready to graph. All right, I'm going to erase our tools here. When you set up to graph a trig function, you don't set up a 10 by 10 window like you did algebra. Because first of all, the x-axis is not in 10 by 10. The x-axis is in radians. So when you graph a trig function, just so you all know when you set it up, your x-axis is going to be way longer than your y-axis. Okay? So when we graph trig by hand, your x-axis is way longer than your y-axis. That's the first thing. To set up your x-axis, you've got to put all these radian measures on the axis. Now, here comes the next problem. You know when you take out graph paper, there are blue lines. And we know when we're graphing in algebra, every blue line means 1 unit. So this would be 1, 2, 3, 4, 5. All those blue lines are equally spaced. Well, the same's with trig. All these blue lines are equally spaced. So when you pull out your graph paper to graph by hand, these blue lines are equally spaced. That means everything's got to go up in the same scale. So if you're counting by degrees, you have to go 10, 20, 30, 40, 50, 60, 70, 80, 90, 100 degrees. It all's got to be by the same units. So if you look here, if we're starting out at 0 degrees, from 0 to 30, that's 30 units, right? From 30 to 45 is only 15. From 45 to 60 is only 15. So look at the spacing. That's 30 degrees apart. That's 15 degrees apart. That's 15 degrees apart. That's 30 degrees apart. So what you cannot do is label this 30 degrees, then label that 45 degrees. You can't say from here to here you can go 30 degrees apart, but yet from here to here you're only going 15 degrees apart. Everything's got to be equally spaced when you graph by hand. So guys, in order to graph this accurately, if you go through the whole list, this is 30 degrees apart between 90 and 120. Then between 120 and 135 is 15 degrees. Between 135 and 150 is 15 degrees. Between 150 and 180 is 30 degrees. If you look to scale everything equally, we're going to have to go in increments of 15 degrees. So each blue line is going to represent 15 degrees. So this is 0 degrees, which is 0 radians. This line would represent 15 degrees. Well, I don't need to mark it because I don't have an ordered pair that has 15 degrees. If that's 15 degrees, this would be 30 degrees. Well, that one I have to mark because I want to plot 30 degrees a half. But I can't mark that as degrees. I have to mark it as radians. So this is I'm going to mark here as pi over 6. So I want everybody to understand why I skipped the blue line. Okay, if we're on graph paper, which is what you should be on, and we're about to set up our x-axis, every line has to be equally spaced. You cannot jump 30 degrees and then jump to the next line and make it only 15 degrees. So I'm looking through this list. The way to equally space everything is to put it 15 degrees. So this would be 15 degrees, but I don't need to mark that because I don't have an angle of 15 degrees to plot a point on. So that's 30 degrees. If I go another 15 degrees, 30 plus 15, that's 45. So I'm going to label that because I want to plot the 45 degree angle. If this is 45 and I want to go another 15 degrees, that would be 60. Well, I want to plot that, so I'll put its radians. If I'm at 60 and go another 15, that'd be 75. Well, look at your t-table. Do you have a 75-degree angle? No, so I'm going to leave that blank. So I'm going to put another blue line. That's 75. Add another 15, that'd be 90. I want 90, so I'm going to mark it pi over 2. The next blue line would be 90 plus 15, which is 105. Don't have it. Leave it blank. The next blue line would be 105 plus 15, which is 120. I have that one. So let's mark its radians, 2 pi over 3. If I add 15 to 120, I get 135. Need to mark that, 3 pi over 4. If I add 15 to 135, I get 150. Need to mark that, 5 pi over 6. If I'm at 150 and I add 15, that's 165. Well, do I need to mark this line? Nope, I don't have a 165. The next line would be 165 plus 15, which is 180. So I'll mark that. So if you see the pattern, look what happened. I skipped one, then I have the 3 angles, then I skipped one, I have a quadrantal angle. Skipped one, have the 3 angles, skipped one, have a quadrantal angle. So it's going to follow that same pattern. That's what makes it periodic. So I'll skip one, and then I'll have my next 3 angles, which are 7 pi over 6, 5 pi over 4, 4 pi over 3. Because think about it. This is 180. Add 15, that's 195. I don't have 195 there. Add 15, 210. Add 15, 225. Add 15, 240. Add 15, 255. I don't have that. That's why I'm skipping one. And I'll put the next quadrantal angle, which is 270. 3 pi over 2. Then I'll skip one again, because if I add 15 to 270, I'll get 285. I don't have that. And the next 3 should be 300, 315, 330. So I'm going to mark those. 300, 5 pi over 3, 315, 7 pi over 4, 330, 11 pi over 6. I should skip another blue line, and the last one should be my 360, which is 2 pi. That all needs to be labeled. Okay? Everybody was with me? So the biggest mistake you guys make is you just take the radians that you have in the t-table and just throw them on there. Remember, those radians represent degrees, and the degrees have to be equally spaced. Now, we're going to label our y-axis. Well, I agree with you. I know where 0 is on the y-axis. I know where 1 is on the y-axis, but I don't know where these roots are. So I got to approximate these to decimals. So we all know 1/2 is 5/10. You guys may not know what square root of 2 over 2 is without a calculator, but I do. Square root of 2 is $1.40. And $1.40 divided among 2 kids is roughly 7 cents. So this is roughly 7/10 for 70 cents. Okay, I'm approximating. You may not know what square root of 3 over 2 is without a calculator, but it's important that you know these facts. We've already discussed this. Square root of 3 is roughly $1.70. $1.70 divided by 2 kids is roughly 85 cents. So for me to graph, you're right, we can't use with the roots. We need to approximate them as decimals. So if you look at your y values, your smallest y value right now is 0, and your largest y value is 1. Now, don't do this. I know on normal graph paper, each line means 1 unit, and we're used to marking that as 1. If you mark this line as 1, then your picture of your curve is going to be so smushed we're not going to be able to see it. So you're going to have to spread this out. So I'm going to, on my graph, make every line count as a 1/4 or a quarter. So I'm going to skip 1, 2, 3, and on the 4th line, I'm going to mark it 1. Well, if you look at our y values, our lowest y value is -1. So I'm going to skip 3 lines, and on the 4th one, mark it -1. When you're graphing trig by hand, do not mark this first line as the number 1, because your graph is going to be so small and swish, you're not even going to be able to see it. Now, all we got to do is plot the points. To make things easier, I'm going to come through and put all my decimals here. So square root of 3 over 2 is roughly 85 cents, approximately. Square root of 2 over 2 is roughly 70 cents. We know 1/2 is 50 cents, 5/10. Over here, all these values are negative. So this is negative 50 cents. This is negative 70 cents. This is negative 85 cents. Over here, we have approximately negative 85 cents, negative 70 cents, negative 50 cents. Okay, so I'm putting all my decimals. So now it becomes fun, because all you have to do is plot all these points and then connect the dots, and you now know what a sine curve looks like. So we're going to go slow. When x is 0, y is 0. What do you call it at 0, 0? Very good, the origin. When x is 30 degrees, which is pi over 6, the y value is 1/2. Well, if we're skipping 4 lines to get to the number 1, do you all agree 2 lines would be 1/2? So at 30 degrees, we're going up to 1/2. At 45 degrees, we're going up to 70 cents, which would be right below the 3rd line, because that's 75 cents. At 60 degrees, we're going up to 85 cents, so that'll be between the 3rd and the 4th line. We're going to leave this blank. We don't have an angle. At 90 degrees, we know we're as high as 1. So let me just fix that so it looks like it's at 1. Move my line up a little bit. 1. Okay? So if you look, it looks like a curve. Now, we're not going to put anything at this hash mark because there's no angle measured. This begins 120. At 120, we're at 85 cents again, so these 2 points should be symmetrical. At 135 degrees, we're at 70 cents, so this point should match with this point. At 150, we're at 1/2, so this point should match with this point. Skip that line because it's not marked with a radian. Go to 180. Your y value is 0. So look, all the y values here are positive numbers. If y's are positive, they're above in the top, above the x-axis. Now we got to do the other half of the graph. So now we know all the y values are negative, so they'll all be below the x-axis. So we'll go slow. We're going to 210, which is 7 pi over 6. The y value is negative 1/2. We're going to 225, the y value is negative 70 cents. We're going in 240, the y value is negative 85 cents. We're going to 270, the y value is negative 1. And then it repeats. At 300, we're at negative 85 cents. At 315, we're at negative 70 cents, so they're matching up. At 330, we're negative 50 cents. And at 360, we're back at the origin 0. All I did was plot my points. Everywhere I have a radian measured label, there better be a point that matches it. How did I know where my points went? I looked at my x values, I converted them. I looked at my x's, which were my radians, took my y values, converted them to decimals so I could plot. Now it becomes a connect the dot. A sine curve starts at the origin, and it is a curve. It curves all the way up, it reaches as high as point 1, and it comes down. Then it goes below the x-axis. It's a curve. Oh. That is what a sine curve is. The practical application of a sine curve is your heartbeat. Your heartbeat goes put-ump, put-ump, put-ump. If you've ever been hooked to an EKG machine, which I have, and you watch your heartbeat, it has a high peak and a low peak, and then it repeats, and then it repeats. That's a periodic function. If I want to continue this sine curve, it would go back. It would go up and go back down. That's why it's periodic. This is the pattern of a sine curve. It goes up, comes down, comes up. Now, I know what you're thinking. You're thinking, oh my, you're telling me in this chapter to graph every trig function, we're going to have to set up a t-table of all these values and plot all these points? No. I did this for a reason, for you to understand the shortcut. This is very time consuming, but it works. Just like you learned in algebra to graph any equation in algebra, you could always set up t-tables, pick as many x values as you want, get as many y values as you want, plot as many points as you need till you see a pattern, something going on. We have the pattern. Now we know what a sine curve looks like. A sine curve is always an up hump and a down hump. The key now is for you to tell me, out of all these points we plotted, which ones are the most important? What are the minimal number of points we're going to need to graph a sine curve? Well, most people would say, well, Miss Black, you got to know where it begins and where it ends. So the question is, if you just plotted the beginning point and the ending point, would you be able to draw this curve? No, because if you just plot 2 points, you know from algebra you would make a line. So 2 points are not enough. What, out of all these points, what are the other most important points you need? Good. You need to know your max and your min. You remember from algebra, max is the highest point and min is the lowest point. So if you plot just those 4 points, would you have enough? No, there's one more point you need. You learned in algebra, it's very important you know where a graph always touches the y-axis and the x-axis. Well, this point here, it does both. It is the y-intercept because it's on the y-axis. It's the x-intercept. But this graph has another x-intercept, and it's right here. So how many points did I circle, y'all? 1, 2, 3, 4, 5. You can graph a sine curve knowing those 5 points only. Now let's look at the angles that correspond to those 5 points. Well, this angle is at 0. That one you need? This high point is at pi over 2, which is how many degrees? 90. This x-intercept is at pi, which is at 180. This min low point is at 3 pi over 2, which is 270. And this ending point is at 2 pi, which is 360. Let's look at those angles. 0, 90, 180, 270, 360. What angles are those from the previous chapter? That's right, those are quadrantal angles. If you know the sine value of the quadrantal angles, that's the 5 points you need to plot to make a sine curve. So, what you need to memorize, and I'm throwing that word out because I'm not joking. This is a memorized fact. You should be able to put this down on paper without even thinking. When I say graph me y equals sine x, you should draw me an x-axis and a y-axis. You should label the x-axis with the quadrantal angles, which are 0, 90, which is pi over 2, 180, which is pi, 270, which is 3 pi over 2, and 360, which is 2 pi. And make sure they're equally spaced. So if you're doing this on graph paper, if you skip 2 blue lines to get to 90, then you skip 2 blue lines to get to 180, then you skip 2 blue lines to get to 270, then you skip 2 blue lines to get to 360. I don't care how many blue lines you skip. If you want to skip 1 blue line, 2, 3, 4, that's fine. What I would not do is label the angles, the radians, right behind each other, because then your graph will be smushed and you won't be able to see it. So when you graph the sine function, the radians on the angles for the angles should be the quadrantals, 0, 90, 180, 270, 360. The y value, well, the highest y value is 1, and the lowest y value is 0. So when you graph a sine curve, the y-axis should be labeled as high as 1 and as low as -1. And again, if you're doing this on graph paper, skip blue lines. If you skip 3 blue lines to get to 1, then you skip 3 blue lines to get to -1. Now, what you got to memorize is the pattern. A sine curve always begins at the origin. At 90, it goes its highest value, 1, its max. It hits back at the axis, so at 180, it's at 0. At 270, it goes to its lowest value, -1. And at 360, it returns back to the axes. Those 5 points get plotted, and here comes your curve. You have to memorize that. Now, in your notes, we have the same thing for cosine. So you now take the time, do the cosine t-table for everything, plot all the points, and then look for the pattern. And we'll talk more about this in the next video.